So everybody okay on these encoders? So this is called a quadrature increment encoder. This is called an absolute encoder. The one you'll run into most often is this guy right here. Y'all understand why it's given that name? Huh? Because it's got two sensors that are all set from each other, right? You understand? And so what we do is we get two signals that are basically 90 degrees apart. And what happens is whichever one occurs first would tell us which direction the encoder's running. So if I'm going to use something that's going to be running in both directions, if I want to reverse it, then I need one of these guys, right? The problem we have with incremental encoders is that they have to be counted to come up with a position or a speed, right? So the rate of these signals coming off, we can calculate the speed. The number of pulses that I have would give me the position. And then the offset would give me the what? Would give me which one occurs first. You understand? Gives us direction. Yeah, sorry. So what we have is we have a motor that's got an incremental encoder on it up here. And it's got a big gearbox on it, so this is what we got to figure out. We'll talk about this as soon as I find the picture. So the incremental encoder is right here, and that's why we got all these wires coming out of this. Because one thing we got a voltage that we can put on the motor. So the motor and the power for the incremental encoder are isolated from each other. So that means we can run them at different voltages, right? You understand? So what I have the ability to do is I've got one of them connected to my power supply over here. Oops. So this is a plus 12 volt supply, a variable supply. So I can use this to control the motor speed. And then over here, the 5 volt supply is running my encoder. But I could run the encoder and the motor on two different speeds because they're isolated from each other, right? Then we have two signals. Let me bring up my other probe, get my scope in. Oops. So this is why we got so many wires coming out of things, because we got. So this is an oscilloscope. Of course, what advantages an oscilloscope have over a meter? Yeah, oscilloscope shows you what's there. So if I put my meter across this, it's going to measure 2.5 volts. It's going to average it out, right? You understand? So it's 5 volts up, 0 volts right here. So what happens for a square wave like this? It would give me 2.5 volts, and all I know is what 2.5 volts. So the oscilloscope shows me what's there. Now what an oscilloscope does is it measures a voltage. So that's all the oscilloscope will do. An oscilloscope can't measure current. But luckily we can't have a current unless we have a what? We have a voltage. So all an oscilloscope does is measure a difference in potential. And so what we have here is we have two channels, so we can actually look at two different things at the same time, as long as they're referenced to each other. And what it does is it shows me voltage relative to time. So this is where I control, we call it volts per division. Can y'all see the major divisions right here? Okay. So my volts per division is 1 volt per division. So I can come up here and count 1, 2, 3, 4, 5, and that's 5 volts. The other thing it shows us is that signal relative to time. So what happens is the scope is actually tracing from left to right, and then what occurs is going to be displayed relative to time. And we call this the horizontal, which is this control right here. And you can see when I change it. So right here, I'm making my scope go slower, so it's cramming more information inside the same thing, right? So this controls the speed, we call it the horizontal speed. And what we try to do when we measure this, guys, is we try to get what we call one cycle on the screen. That's when the scope is going to be more accurate. And then what I can do is I can take my horizontal position and I can move it so it lines up with a vertical line. So now so time moves from left to right. So I'm going to start this right here, right? Does that make sense? I've got it on 100 microseconds per division. So that would be 100, 200, 300, 400, 500, 600, 700, about 750 microseconds. Now another way people do is they use their calculator. I like to count them because I understand it. Is you count the number of positions. If I count in ones, can y'all see the little minor divisions right there? Well, if I count in ones, so these are the major divisions right here. This little dot right here is minor divisions. So that means each minor division, if I'm counting in ones, then each minor division would have to be worth a 0.2. Does that make sense? So I could come up here, I can say 1, 2, 3, 4, 5, 6, 7, 0.2, 0.4, and then I can multiply it by that, and that would give me the time. A lot of people that's first to using scopes, that's what they do. And I would do the same thing here. So what I'm going to do now is I'm going to turn on the other channel. I'm going to take this guy, I'm going to make it smaller, and then this is the position control. Y'all can't see what I'm doing. Oops. So this is the position control, and what I'm going to do is I'm going to take this one and move it up to the top. And I don't know if y'all can see the 1 right there, but this shows me this is 2 channels. This is channel 1. And then I'm going to turn on the other channel right here, and this is channel 2. And you can see I'm referencing the channel 1. We call it the trigger, so you got to reference one of your scopes. The problem we have is this is taking a waveform. This is taking a waveform, and now my scope is not in sync with the waveform, right? You understand that? So what we have to do is we have to give the scope a reference that we're going to reference to. We call this the trigger. So I'm going to bring up the trigger. And you can see what I'm referencing. I'm referencing one of the edges, which would mean either the rising or the falling edge. I'm sorry, I didn't turn it on. That wrong thing. I did something wrong there. So I'm referencing the what? An edge. Which channel am I referencing? I keep hitting auto, guys. I'm hitting the wrong button. I'm referencing channel 1, and I'm looking for a positive going slow, right? Does that make sense? So notice, here's my trigger. Y'all see the little arrow right there? And what I'm going to do is I'm going to spread it back out. And you can see no matter what I do, whatever I do, that edge is staying what? Right there. Okay. So here's my trigger is saying, okay, I'm looking for it to get up to that voltage up there. Well, this is what would happen if I didn't reference the scope to the signal itself, right? You understand? Huh? No. This would be like me up here writing letters on the board. And you just randomly open your eyes like this. And I might be between the letter, I might be between a word, I might not be anything. So what I would do is I would come up here and I would write a word, and then I would go boop, beep, and you'd do what? You'd open your eyes. And now you're in sync with me. So what's happening is I've got a waveform that's occurring. And my scope has no reference on what the waveform is. So this would be like you just doing what? Randomly open your eyes and expecting to have a whole word up there. So what we do on these repetitive waveforms is we reference the scope to one of the signals, either what? Either channel 1 or channel 2. I've referenced it to channel 1. And then I've referenced it to the rising edge. And then this guy over here says T. This is the level I'm going to trigger on. Well, right now, I've got my T adjusted above the waveform. So now my scope is, we say it's out of sync, it's out of trigger, right? You understand? Because I'm not referencing anything on the waveform. As soon as I get my trigger level down in channel 1, As soon as I get it into, now my scope freezes. But notice it freezes exactly where I'm triggering from, right? You understand? That makes sense? So what we do with the trigger is we have the ability to reference our trigger, our waveform. Like your TV, guys, your TV is doing what? It's flashing pictures. Well, the camera is sending synchronizing pulses to your TV to tell it when to do what? Yeah, it synchronizes. If I didn't synchronize that, in the old days, we had what we call a horizontal hole and a vertical hole. I don't know if y'all, and what you were doing is you were doing exactly what I'm doing here. You actually were setting the triggers so your TV would be in sync with the camera. So your camera's taking pictures like this, and let's say your TV is doing this, right? Y'all understand? So what do? Well, they send these synchronizing pulses. We call them horizontal sync and vertical sync. And what that does is now your TV is synchronized with the what? So when my camera's doing this, my TV's doing this, and when my camera's doing that, my TV's turning off. So guys, your TV is flashing at you. We call it, in computers, we call it a refresh rate. So that's how fast my images are being displayed, right? You understand? But if I didn't have a method of synchronizing something over here with something over here, then if your TV and your TV would be rolling, it would be flopping over, it'd do all kinds of weird things. So you can tell when you're having problems with your sync because your TV will start doing what? Start rolling. And then you now used to in the old days, you'd go up there and change the trigger, right? The new days, it means you got a problem with the electronics in there somewhere. So what I'm doing is I'm synchronizing right here. So what I can do is I can move that over. So what I'm doing is I'm going to take my position and notice my reference is moving with it. Can y'all see that? So what I can do now is I can come up and I can move it so I put that vertical line on the starting line. So what would be the speed of the motor? So if I was going to figure out a program, how fast is the motor running? I'm not fast. How fast is this shaft running over? Can y'all see it turn? So how fast is it turning? Well, I could start a stopwatch and I could count the revolutions for a minute, right? But a PLC couldn't do that. PLC is going to have to count these pulses coming off those encoder and then use those to figure out the speed. So anybody got any ideas? So I'm looking at my scope. Okay. So this is the output of the encoder. I don't need channel 2. All I need is one of them. We could get better resolutions, by the way, if we count all the edges, but it's not going to change the speed. So what I'm going to do is I'm going to get rid of channel 2. I'm going to turn channel 2 off. And then that's going to let me to make this thing a lot bigger. So I'm going to put my 0 reference down there. Of course, I went out of trigger, right? Because my trigger's up here. So how fast are we going? Well, yeah, we could do what we call the period or the time for one cycle. So that's the first thing that we would work on. So let's make it even. So I'm going to speed my motor up a hair. I'm going to slow it down a hair so it works out perfect, right? So now we got 100, 200, 300, 400, 500, 600, 700, 800 microseconds. Okay. So somebody write this down. What's the next thing that we need to know? That's not going to give me speed. This is an encoder. Right? You understand that? I got that. Exactly. We need to know how many pulses we're going to get for a revolution. Right? Because we're not doing one of these guys. So what we're doing is we're measuring one of these guys right here. We're measuring the time for one of those guys right there. So what we're doing is we get a pulse out right here. Let me stop this. So what we're doing is we get a pulse out right here, and then we're waiting on it to get the same place on the next pulse, right? You understand? So that would be the time for one of these little dashes right there. So the next thing I would need to know is how many pulses do we get per revolution? So we need to know the encoder. We need to know what the encoder gives us. So what we'll do is we'll bring up the data sheet on the encoder. This is not wrong. So this guy goes through a gearbox. So what it does is 131.25 to 1 metal gearbox. So what happens is that it takes the output of the motor and divides it by 131.25. And of course what that means is that I'm going, so work in should equal work out, right? You understand? So work at work, physics is force times distance. So what happens, if I run it through a gearbox, we can do one of two things. We can increase speed and decrease work, right? You understand? Or we could do what? We could decrease speed and increase work. Or sorry, increase torque because we're dealing with a motor. Right? You understand that? So what we're doing is we're taking the speed of the motor and we're dividing it by 131.25 gearbox. So what that does is what we have, it says, right here it says 12 volt motor, right? You understand. It says we could run it higher than that, but we don't want to do that. So the motor is in 12 volts. The geared box are functionally identical in previous versions. We need to do that. I'm missing something, guys. Oh, right here. The generator is a 12 volt brushless DC motor, metal gearbox, and a integrated quadrature encoder that provides a resolution of 64 counts per revolution, which is 8,400 counts per revolution of the gearbox. This unit has a 0.65 stem. Okay, so this is the ratio between here and this, right? And I said, okay. And I said, okay, I'm getting 8,400 counts per revolution. And then everything didn't work right. So guess what? I had to read further. Two-channel Hall effect encoders is used to sense the rotation of the magnetic field of the motor shaft. The quadrature encoder provides a resolution of 64 counts per revolution of the shaft when counting both edges of both channels. So we're not going to count both edges of both channels, so what would that give us? 32, right? Or would it give us 32 or would it give us 16? Well, we're not counting both edges of both channels. We're counting one edge of one channel. 16. Okay, so we get 16 pulses per revolution of the motor, and then we run that through a gearbox that's got 131.25 gear ratio. So I take 16 and I multiply by 131.25, and that would give me the number of counts I would get per revolution of the output shaft, right? So what does that give us? Should give us 16,000 counts per revolution. 1,600 counts per revolution. Is that right? 31.25. What's that? Something's going wrong. Huh? Well, what we're trying to do is, when we talk about the output of the shaft, So I don't know if y'all can hear this or not, but the motor is running a lot faster than the shaft because it's going through 131.25 gearbox reduction, right? So the motor's running a lot faster than the shaft. Well, see, our encoder's back here, so the encoder's on the motor, but we need to know the speed of the shaft, right? That makes sense. So we get 64 counts. If I was to come up here, and I was to come up here and put both these up here, and I was to put both of them up there, and I was to come up here and count all the edges. 1, 2, 3, 4. Y'all understand that? The time for that. We don't need to do that because, first of all, it's a little harder, but if we can do it, if we can divide it and get it what we get for one counter, then we can do the same thing, right? Understand? So I would have to come up with a circuit that not only counts this edge, it also counts that edge, and counts this edge, and counts that edge, and counts this edge, and counts that edge, right? Y'all understand? So I could do that on my oscilloscope, but what I'd have to do is I would have to get both of them over here, and I would have to figure out how to get both of them up there, right? Spread it out as far as I could. And get one of the blues and one of the greens, and then I could come over here and overlap them. Oops, and I lost my trigger. Then I could count, then I could come up here and count this between here and here. Right, you understand? And then I will multiply that by 2. Because I'm only looking at one pulse, but it says both pulses, right? So we're going to count the rising. So 1, 2, 1, 2, 3. Sorry. 1, 2, 3, 4. You understand? Yes or no?
Count the rising, but
no, we said both edges. So what I would do is I would start with this rising edge, 1, 2, 3, and I'd go to that rising edge, so I get 4. So if I measure this time right here, which this is the best I can do, then I would multiply that by 2 to take care of this, right? Okay. That makes sense? But if I'm only going to measure this one, then we could just take that and divide it by 4, right? Understand? Yes or no? Well, we could do the blue or we could do the blue or the yellow. I'm triggering on the yellow one, so that's why. If I turned this one off, then the scope would probably go out of trigger, right? You understand? So normally we just use one of those. So what we're saying is if I came over here and if I counted 4, I could divide that by 4, and that would give me the time for one of them, right? Or I could just measure the time for one of them. So what they're saying is, but I wouldn't use 64,536 counts. I would use 82,000 counts. I'd use 82. Let me go back and look at it. I would use this 84,000 counts, and I would divide it by 4. We take that and divide it by 4. What do we come up with? Okay, so I've got this wrong. So we get what? 21,000. 21,000. 2,100, I'm sorry. All this don't make any sense. Then I could use it to sense position. So if I was going to use it to sense position, then I would take the 21,000 and then I would divide that into 360, and what answer would that give me? I'm sorry, 2,100, yeah.
5,183.
360 divided by 2,100. Ain't gonna come up and be no 5. Might come up and be point. Plus point what? So that'd be 0.76. What is it? Say 7.6. What's that?
0.171.
So it's not going to be equal, but this is okay. That would be degrees per count, right? You understand that? So that's pretty accurate. But that's if I was going to use this to sense position, right? What we're trying to do is figure out the speed. So what we're going to do is we're going to come up here and do what? Measure the time for one cycle. Then we're going to multiply that times the number of pulses per revolution. So that would be 2,100, right? Then we're going to take the reciprocal of that, and that's going to give us our rotations per second. And then we'll multiply that by 60, and that'll give us our revolutions per minute. Y'all understand that procedure? I hope so, because there's one of these on the there's one of these on the Siemens test. It will be. This guy right here, this is the data sheet. But it should make sense. And by the way, they popped this question up. They popped this question up on when we was at level 1 training, and I missed it.
What it says, okay, I know it says multiply by the number of pulses.
Yeah, because what we're doing is we're measuring the time for one pulse. But we get this many pulses per revolution. Right? You understand that? So our scope can't measure the number of pulses in a revolution because we'd have it all crammed up there. We wouldn't be able to see anything. So what we're doing is we're measuring the time for one pulse. So what we do is we multiply that by the number of pulses we get per revolution. The problem is my scope does not measure in minutes. My scope measures relative to seconds, right? Y'all understand that? So what we do is we measure the time for one cycle on our oscilloscope, and then we multiply that times the number of pulses we get per what? For one whole revolution. Then we go from time to frequency, we take the reciprocal of that, which means we divide it into 1. Because time and frequency are just opposite of each other. Does that make sense? So that gives us our RPMs per second. We don't want RPMs per second. The scope measures in seconds. We're trying to get RPMs per what? Per minute. So we take our RPMs per second, and then we multiply that by 60, and that will give us our RPMs per minute. What would we do in the PLC? We would go ahead and find these two guys right here. And just multiply by one number. So here we go, guys. Everybody got that down? Okay, so I'm going to bring my scope back up. And I'm going to get rid of the green because we're not using 8400, we're using 2100, right? Get rid of the blue one, excuse me. And we're going to come up here, I'm going to turn this off, and I'm going to measure the time for one cycle. So what's our time? I got it on 100 microsecond per major division. I got 1, 2, 3, 4, 5, 6, 7, 8 divisions. That's 800 microseconds. How many pulses do we get per revolution? So this is one pulse. We get 2100, right? You understand? So what am I going to do? 800 microseconds. I'm going to multiply it by 2100. Then I'm going to take that and do what? Take the reciprocal of it. No, we got to get it from time into frequency, right? Or speed. So what we do to go from time to speed is we do what? Take the reciprocal of that. That will give me my revolutions per second. Then I will multiply that answer by 60. And how fast does the motor go? Per minute? 35 what? 35.7. So we could put a stopwatch on here and we could count them. The 0.7 would be hard to do. But we could probably do 37 pretty easy. Huh? Yeah, you can, yeah, the dent, that's what we would do. So all we do is we reference the dent, and then we can put a stopwatch on there, and it should be about 37. We should count about 37 in a while. In a minute. That looks good. That looks good, guys. I mean, are you ready to do another one? What I'm gonna do is, of course, you can see as soon as I turn it up, time goes down, right? So what I'd have to do is I'd have to turn my scope. And I need to see, I'm going to come up here and change the position until I see both a rising edge and a falling edge. Right? Let's see if I can get it on there. I might have to drop down one. It's going to be close. Oh, yeah. Then I'm going to line it up with a vertical line. I got it on 25 microseconds per division. So there's my time. Can y'all see the time? 25 microseconds per division. So that's this way. So I'd come up here and count the number of divisions. So how many divisions do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.2. 10.2 times 25 micro. Then we'll take the what? Typical that, and then we multiply by 60, and that should be the speed of the shaft, not the speed of the motor. This is the speed of the shaft. The shaft is what's doing the work, right? You understand? Huh? What's that? Well, probably it's wrong. So what we got? So we had what? How many divisions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.2. I'm going to take 11.2. I'm going to multiply this. What's that? I'm going to multiply this times the time per division. 25 times 10 to the minus 6. This gives me my time. Right? I'm going to multiply that times 2100. Which gives me that. I take the reciprocal of that. Multiply that times 60. So that's the speed. Y'all see what I did? So this is about right. Huh? Okay, so what I did is I counted the number of divisions. This is the way most people use the scope. Is I counted 11.2 divisions. Because if I'm counting in ones, if I take 1 and divide it by 5, I come up and get 0.2, right? So that means each minor division would be worth a 0.2. Everybody okay? I want me to bring the scope back up and let y'all see it.
Yeah, bring that up.
I'm not going to bring it up full screen because we can see enough of it here. So 25 microseconds per division. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I just counted wrong. 10.2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't count. Thank y'all guys. So what I'm going to do is I'm going to come up here and clear this out and do what? 10.2. I'm sorry. 10.2 times 25 times 10 to the minus 6 equals that.
Yeah, he raised page 20 this morning. Oh. 25.
So I got 10.2, right? And I multiply that times 25 times 10, right? So negative 6. That's what I got. It's 10.2. That's what you're forgetting about. And then I'm multiplying 10.2 times. It's 25 microseconds per division. Okay, that's my fault. 25 microseconds per division. Okay, all right. Yeah, 25 times 10, so I understand y'all's confusion now. To the minus 6 equals that. Not yet. I'm going to multiply that times 2100. Then I'm going to take the reciprocal. And then I'm going to multiply this times 6. About 1200 RPM, right? So yeah, that would make a big difference. Yeah, I don't know. It might be hard for y'all to see. See the little decimal point right there? Yeah, it's that. So that's what I couldn't understand how you was coming. All right. So we okay now? So any speed. I mean, I could put anything up here, right? You understand? Or I could go ahead and take I'll have to figure this out. We could figure out the actual fraction. So we take the reciprocal of it, right? So I could go ahead and take 2100. Then I can take the reciprocal of that. Let's see if this works out. And multiply that times 60. What was it? I don't know. I have to figure it out. We could come up with one math formula where we could come up and just do everything with one formula instead of doing everything that we just did. I want to do another one. So we'll change it. Well, I've got it running pretty close to its limit. So what I need to do is I'm going to take my scope and I'm going to slow it down so we see one, so we can see one cycle, right? But then what I'm going to do is I'm going to take my horizontal position, I'm going to put it on a vertical line. So right now we got it on 50 microseconds per division. So what would be my speed? Huh? Oh, fuck. Why did that make a difference? Well, you don't need that line. All you need is this line, and all you need is that line. You don't need that line in the middle. So what we're doing is we're counting the time for one whole pulse. So this is the time between pulses right here, right? Understand? Per division. Yeah, I don't know if y'all can see the little decimal point right there. See the little decimal point right there? So what we got?
And 4.7 RPM per.
Huh? Y'all probably can't see this. This is in the middle.
0.6,
0.65. No, it's 6.65.
6.
0.65.
Yeah, y'all can see it pretty good compared. See, this is not on that line, and it's not on that line. It's really close to the center, so I use 0.65.
But if you Sally, you were really close. I mean, 75, that would have been okay too. I mean, even if you take this and round it, it's going to be 75, right? Yeah, it shows up really, really well up here.
It shows up really well.
Except it's a little lopsided because my camera's lopsided. I don't know what it is. I lost the other edge. There we go. I wonder what that little pulse is right there. This is a really, really clean encoder. We have one of these on the Amatro line. We have one of these on the Amatro line, and it's a quadrature encoder. It don't need to be a quadrature encoder because it's only, the motor only runs in one direction. So the only advantage a quadrature encoder has over well, it's got two advantages. if you count all the edges, then you get better resolution, right? You understand that? So instead of using 2100, we'd use 8400. So you get a lot more, a lot less degrees per edge. But they're not even using it. So, but what we would have to know is, first of all, before I can even use it for position or before I can even use it with speed, I would have to know how many I have per revolution. So right now we don't know that. We'd have to go over there and get the part number up and look it up and see how many pulses we get per revolution off those things. But it's basically the same thing. Now, whether that uses Hall effect or whether it uses optical encoders, that really don't make any difference to you, right? You understand that? Because all you need to know is I don't care how the pulses come out of the thing. I don't need to know how they're generated. I just know I need to know what I'm looking for. So a quadrature encoder, you're going to have at least you're going to have what they call a channel A and a channel B. Which one's channel A and which one's channel B? Whichever one you choose, right? And then once you figure out which one's channel A and which one's channel B, but this one's labeled, by the way. So if we follow this on down, this is the actual wiring for this. No, it's not. No, I'm sorry. So A encoder is the yellow wire, and B encoder is the white. But it all depends on which one you want. So which one would be forward and which one would be reverse? It's up to you which way you reference it, right? Does that make sense? You know, so and forward and reverse on a motor is a arbitrary thing anyway, right? So which way is forward and which way is reverse? Is it clockwise? Which way is forward, clockwise or counterclockwise? It's whatever you say. It's what you hook it up to. What's forward? Of course, in an elevator, it wouldn't be forward and reverse anyway. It would be what? Up and down, or it might be left, right? So forward and reverse are arbitrary terms on a motor, especially when you go through gearboxes, because gearboxes change directions, by the way. So if the motor's turning this way and it pushes against the gear, then the motor's going to be turning this way, gear's going to be turning in the opposite direction anyway, right? You understand? So every time you go through a gear, it's going to do what? It's going to reverse directions on you. So forward and reverse are relative terms. So one way is going to be forward, one way is going to be reverse. And, that's one of the things that we'll look at when we get into motors is how do we reverse these? We don't say it's the reverse direction. Reverse means it just changes what? Changes the direction that it's currently going in. So I could say if it's going this direction, I reverse it, it would go what? Counterclockwise. If I reverse that, it would go what? So we call these circuits reversing circuits. So, we'll look and see how we actually reverse motors, and we'll go over there and see that. So glad, I don't know how I came up with 1600 guys, but y'all did a good job on that. There's the basic procedure. All right, we're getting out at 20 after. We're taking 30 minutes, right? So y'all go ahead so what time do we need to come back? 10-2? Coder on our manufacturing line, and it's a TRS 100BD. Y'all see that? I need to blow it up. Yeah. Which is the very first one. So it gives us what? 100 pulses per revolution. It's an NPN open collector. So when we generate a switch, these are DC devices. So usually when we switch DC devices, we're going to use either what we call a P. We're going to use a relay output, right? Now the problem with relay outputs is they can't be real fast. So normally what we do is these sensors, when they switch DC, they usually use what we call BJTs or bipolar junction transistors. And what we look at is, and we're operating these things like switches. So we have two types. We have what we call an NPN. Then we have what we call a PNP. Basically, you look and see which way the arrow is pointing. So the arrow always points toward the end, right? You understand? So this would be an NPN. And so this is P in the center, so this would be what we call a PNP. Now let's just see if y'all's paying attention. So it points toward, the arrow points toward the end. So here the end is in the center. So this would be what we call a PNP. So normally, when we talk about sensors, we talk about syncing and sourcing. Everybody okay there? And so normally an NPN sensor is a syncing sensor and a PNP is sourcing. What they're doing here is, and we're operating these things like switches. So this would be like I come over here and I've got a switch. So it's NPN. So this right here would be common. And then I have a switch. And then open collector means I bring this out right there. Now, I've got the negative right here, so what are we looking for to complete a circuit? Okay, but I can't just use a positive, right? You understand? I can't just use a positive. I gotta have a load, right? So a circuit's gotta have a load. So what we have to do and this is what they mean. So this is the collector right here. That's the name of that lead. This is the emitter. And this is the bulb. And what a transistor is, it's a current valve. So we can make it operate by a switch, but it takes this is the valve control right here. So we can put a little bitty small current into the base lead, and it'll open that valve wide open. And this is our main valve right here. But still, we got to look for a load, right? You understand? Now, normally on a NPN sensor, then the load will be the input to the PLC itself. So the input to the PLC represents a load. But what they're doing here is we've got to come up here and we've got to do this like this. So we got to put a resistor up there. So that means if the switch is low, if this is up here is 24 volts. Then if the switch is closed, I would get 0 volts out. If the switch is open, I would get 24 volts out. That makes sense? Okay. And that's what they mean by open collector, which means the collector does not have that resistor in there. We got to do what? We got to add it either through the PLC. So the input of the PLC or by putting our own resistor out there. Does that make sense? So let's go over there and find this thing. On my, I need an extension cord. What I'll do is while y'all unlocking it, I'll come up and bring stuff. So this is our logic for what I would have to do is I have to calculate, or I make the example, and I have to take the number by 5. Then I would know this kind of number fail to move one cell, right? That's why here's the actual. Here's our power. We call it secret. A lot of people like to say,
permit to replace these plans on industrial use. It's very good. Allows solid. But the actual one to look at, another from what that's all one. Both of them, both of them, but that's what that line. That's what we do, verify our. That same thing. So we could calculate the fee. Calculate. So what we're gonna do now is we'll come back to your verify, normally we verify on house, don't verify. The only time we have to verify the power supply, that's locked out, and verify. This guy right here, he's on four, he's on the Tesla line. Here's the Tesla line. This is what's called. What we do is lock out. We got lockdown. Thankfully, these are not all. You know, some people actually build things to actually be able to lock out things. So these are plug doors. This looks like this. section. Or that's what it is. Looking forward, even and what you can find. Like I said, what we're ready to do? We're ready to fire this puppy up. So what we're gonna do is finish up our lap. I don't know if I did the lap. Okay. Tell them here, you don't put. No, he said give one of us. I need to check like this room okay first.
Okay, yeah.
If y'all get trying to be slick, if y'all get trying to get up and get drowned. That's what it is. Yeah, they need to keep it.
You want to let us?
No, they need to. Y'all get trying to get drowned. We probably. Yeah, not probably. If it were, probably.
Okay, guys, y'all just start over. They'll turn up when I'm not looking for them. I don't know if we had any extra lap forms over there.
I need to check that I did it right before I go any further. Or do you want the whole thing?
No, I want to check it. Wait, I can't check if it's put on right. The next part.
I need to laugh. Like this. Y'all are only three that like it. No one else like it. What that is? You got your own? Yeah. He's up again.
Y'all need to grab that. Oh, wait. Got one more foot.
You got it?
So you must have carried it home. So the solid state got put on top of it.
Procedures for taking it off.
Mhm.
Can I go ahead and take it off? And it doesn't matter which one I take off first, right? Right.
Not according to our lab. So if your gearbox steps up speed, then you lose force, right? If it reduces speed, then you gain force, right? Everybody understand that? Well, in force on a motor, we call it torque. We call the force a motor generates as a torque, because it's a twisting, turning, right? So instead of me saying force, I would say torque if I was talking about a motor. If your gearbox increases speed, you get less torque, right? Somebody from Lawson Stage trying to come. This is Rick talking.
Hey, Nancy, I just found out that you were So everybody, y'all find y'all's lab? You find your lab?
Okay, I'll run the lab off. Wait a second.
I'm sorry.
I got this.
I mean, sorry.
I said, well, I've got this on my mind. Good gracious.
I didn't find how to remove it there. I don't see it on that. I don't know under another side somewhere.
So, we had a tour come back through yesterday. In fact, there was an interview in Allison. And so we had to remove y'all's locks. Hopefully they're back on their line. Well, they did some type of interview, so it was some type of news agency or something. That's what I told her. She got kind of upset. But this is not work. This is school. So that's why we keep the keys, right? So in the work environment, guys, nobody's gonna have that key but who? But you and maybe your boss. So when I worked at US Steel, we had 2 keys, and the bosses had a key box that they kept locked up. It was locked up, where they kept the second set of keys in there.
How about so you got what I have in the folks.
Yeah. From what I understand at US Steel, that's what they have now. So from what I understand at US Steel, it's one key. And then if that's what happens, the second key would be a bolt cutter.
with, to verify that, module is working. How would, I mean, I know I put
You're
it
not
all.
going to everybody to watch. So here's our actual lockout tagout. This is what Anthony was talking about. So you come in and actually put this on the light switch. And then you put it in on or off. Normally the switch is off, should be mounted. It's a single pole switch. It should be mounted so down is off, right? You put it in that and you close it and you lock that. So light switch. I showed you the plug forward. Here's lockout tagout. I don't know what that guy would do.
Wow.
That's nice.
That's over 30 yards, you put it in, lock out who you want.
So here's a lockout this is some type of lockout. Here's some type of lockout. That's about the same plug our 440. We have lockouts. This is some type of. Oh, this will work. The other side is on the They're not. Oh, yeah. That makes sense. Yeah, we got light, we got tag, lock.
If you're guys school with Veteran Day, you know Veteran Day is on a Sunday.
What about it?
Are we out of school Veteran Day? You know Veteran
Be on
Day
the
is
college calendar. Y'all know where the college calendar is, right? So you go to Lawson State website. not on this one. And then academic calendar. Veterans Day is November. We'll get on 12. It's also on our calendar too, by the way. So what I do right off the bat, first thing I do when I develop the course calendar is I put all the holidays on. So we do get that money.
Oh,
You're no veteran.
It was Joe. I said, Bill. If you were.
So it sounds like Trump is sending active duty people down to 200 people. Troops.
They're pulling guards when you go to the border. I told
Well,
you.
they said the guardsman, but they, from the way I got the indication, he's sending active duty down.
Border too.
It's 200.
I know from my old unit, I think I transferred back to my other unit. Pulled 42 people from my old unit. Go down and
I thought that they had to get a state before.
Yeah, that's what they asked. They asked the states. They asked the states to do it, and a lot of states did. But you're right. The National Guard is.
They got on the paper. They got on the paper. They said they were
Yeah, but they send active duty down there. We're paying for that. And them guys, those people are still over 1,000 miles out.
that's all they can. They got other means of way to get in.
They're 1,000 miles away. How long do you think it's going to take them to get here? They just got to camp out on the board for all paying in the field and be on the board for 10
Bunch of active duty military people on the border with nothing to do.
Well, a lot of guards, they volunteer to go because, like you said, they get an active duty check.
Oh yeah, I can understand that. If you make more active duty than you do when you're working your job,
Yeah.
and your job can't fire you.
They can't fire you.
So what they gonna do when the people get there? They gonna arrest them?
Well, the guard can't. The military can't.
That's what I know.
But what they can do is they can watch and they can report it in. So we're sending helicopters down there. They're not telling how many drones they're gonna have flying down there.
They still 1,000 miles away. Doing 15, almost a month when they get here.
Yeah, but they got that group coming. There's another group that's already started up heading this way, and then there's a third one that they're trying to organize. So,
You saw that tunnel they found the other day? They had the lights all the way through it. It was from right
somewhere.
outside of Tijuana, San Diego. It had lights in it. They had this rail system in it. You laid down the thing, shot back in it.
It went all
so
the way
sweet.
underneath San Diego.
Yeah, it was sweet. It looked like a ride or something at Disney World. Yeah, they had lights all the way through it. They was powered up and everything.
And downtown they have from
They so bad. They sound so
all the way in,
sophisticated. Tone.
Yeah.
San Diego. They came up in a warehouse.
Smuggling drugs.
Smuggling goods.
Yeah, they said it was
And
drugs.
people too.
They was moving bricks.
We ready, guys?
Oh,
They moving
wow.
bricks.
Yeah, we gotta get to work. We talk all day long.
Well, I got which one my cat. My new
Well, we got election coming up next Tuesday.
Voter. Hey, that's the big right. First rule, do no harm, right?
Oh, who was ducking God. She won't even debate nobody. I got number 5.
Okay, everyone, take my